it's very similar to working with z-values and
Yeah.
deviation, right? But it's just when we don't know the whole population, we're just working with samples. But what confuses me is how can we come up with, I'm trying to think of the right way to phrase this, how can we come up with data that confirms or disproves a hypothesis if we are really unsure about if the sample is representative of a population? That's
I mean, that is an important thing, because we make an assumption.
okay.
Right? Stats makes an assumption that the samples are representative of the population. That's a basic.
And does that come back to just choosing a large enough sample size, a random enough sample?
Yeah, you do a random sample as well as you can.
Mm-hmm.
It's almost impossible to do random samples in social sciences.
Mm-hmm.
And it's almost as difficult in medical sciences, because you typically aren't dealing with well people. You're dealing with populations of sick people.
Mm-hmm.
And so you don't necessarily have totally representative populations. And the best you do in the medical sciences, when they're getting ready to do a big experiment, they do that double blind thing, where you have a population that is not random, because it's all sick people. It's people that have a certain condition or have a certain propensity for a certain condition or whatever. And let's say you're looking at something that helps weight loss. Well, you're looking at a population of people that are overweight.
Mm-hmm.
And that's basically, so they're not representative of the general population. So it's you kind of define the population. And if the population is people that are overweight at a certain level or whatever, then that's where you start.
Mm-hmm.
In the medical fields, then you can do the double blind thing, where you randomly divide them. And then, half of them get a placebo and half of them get the treatment, or, that sort of thing. And nobody knows who's getting what. The doctors don't know, the clinics don't know, the patients don't know. And so they don't have any way of biasing their response to the treatment.
Mm-hmm.
And that's about as close as you get to random. In the social sciences, it's almost never truly random. Now, for a t-test, for like independent t-test, which is the one that's most concerned about that,
Mm-hmm.
most concerned, because you're doing a one sample, you're not really worried about whether the one sample is representative or not, because you're comparing it to a population parameter that you've gotten from somewhere. Like the national average for something is this. Is this group different? Well, you're not worried about whether that group is random then, because you're really comparing to see if they're not random yet. That's what you're trying to say. Pre-post, it's the same group, so it doesn't matter. You're not really caring about whether the group's random or not. But when you do the two sample, the independent t-test, you're making an assumption. You're actually making two assumptions. You're making that they are drawn from, the two groups are randomly drawn from a randomly derived population. And that's almost never exactly true. And so, in almost all cases, you're violating the assumption to a certain extent. It's just a matter how big.
Mm-hmm.
The two sample t-test, and we haven't talked about this, so I haven't really gotten into this yet with the class. The two sample t-test runs what's called the Levene's test, and it's really a test to kind of estimate whether these two groups might be drawn from the same population or not. And if that Levene's test is significant, mm-hmm. then you use one set of significance levels. If the Levene's test isn't significant, you use the other set of levels. But for the type of data that we're using right now, those are almost identical.
Okay.
We haven't made that distinction yet, but we'll get back around to that because you know, it does come into play when you get bigger samples and things like that. You have to know, you know, are these things relatively the same, like they're drawn randomly for the same population, or are they unique enough that maybe not? And then there are other techniques that we'll get to later on called logistic regression, in which you can figure out whether, you know, two samples are biased and kind of remove all that biased effect and figure out whether they're different or not. So there's way to correct for it, but yeah, we make that assumption in all of these inferential statistics that these groups are randomly drawn from a random population, and it's not a matter of whether we violate that assumption, it's a matter at what level. And that's probably why you always never ever say that you have proven anything or that you're 100% sure about something, because you always have that little ambiguity hanging out there of, you know, well, we're not sure that they were randomly drawn.
Okay.
But it's close enough that, you know, we've kind of lived with that for 170 years, so you know we're kind of good with it right now. But yeah, there are other statistics that are a little bit more complex that allow you to sort those things out a little bit better. And if you're getting into some big major research project, you're going to be doing probably something like that, as opposed to just saying, are these two things different from each other?
Okay. Okay. That makes it. So when you do a paired t-test, you're always using the same group. It's just at a different point in time.
Just different point in time, and maybe a different measure. I mean, sometimes you might have two measures that are two forms of a test. You know, you may have a form A and a form B that, you know, the questions are randomly drawn from the one question set, so that you can have an A and a B, and you can't, you know, what people responded to on the first one won't bias how they respond on the second one.
Okay.
You know, that in once again, I'm kind of, you know, later on we'll be talking about bias effects, and that'll be one of those bias effects. But yeah, and most often it's the same, something measuring the same thing in the same way. But it is possible that it could be two different instruments looking at the same concept, and their scales are the same. So, you know, it varies a little bit. Yeah. But you're assuming now, yeah, that it's the same instrument. Yeah. Okay. Or one that's exactly similar to the other one.
Okay. That sounds good.
These are all good questions. You're not supposed to ask these quite yet, but these are for future videos. You know, I got.
Well, good. That's good.
I got to save these videos for later. I won't have anything to do with this class, so yeah. So I don't want to get into it too much. But
this is kind of a maybe random, maybe not kind of question. But you know, in talking about like the t values and then z values, I know there were the tables, like the defined.
Yeah, well, we still have them. They're in the back of stats books. Yeah.
Right. And I remember seeing those in my undergrad stats class, which I really unfortunately did not absorb much of at all.
Nobody ever does.
Yeah, it was interesting. But anyway, is that something that we will need to draw? Okay. Okay.
Because I mean, these days, I mean, you can run simple stats on your phone.
Oh, okay.
Yeah, you can just ask Google, you know, is there a significant difference between these two groups with these, you know, 10 numbers in each group, and Google will tell you. And so it's, you know, it's almost impossible to have to use those anymore. Now, if you were out in the middle of the wilderness, you didn't have wireless, and all you had was a stats book. Yeah, but I think you would probably figure it out.
Is that the case where you would do the, you made a point that this is not really a math class, it's more about logic, but is that the case where you would do the equation and then
Yeah, you
look
might
at?
actually have to do I was telling Jesse earlier that I actually have a book over here that I had to have in my second or third stats class 40 years ago in my doctoral program that was a computational handbook of statistics.
Wow.
And it had every formula in it for about 75 or 80% of all the statistics. And some of those formulas would stretch over a page or two. And it would you take this value and plug it in here, and you take the mean, you plug it in here, we had to do a few of those just to get so people would understand that we actually could do the math part of it a little bit. But nobody ever does that anymore. And if people do, it's because they don't quite understand the logic of it.
Okay.
And they feel comfortable with the math, but not with the logic.
Okay, that makes sense. With a p-value, is that the percentile, or a way to think of it?
Yeah, you can think of it as a percentile. You can also think of it as a probability.
Okay, that makes sense.
Those are not
out of one, right?
Out of one.
Okay.
There's and you want the p-value to be less than 0.05.
For it to be significant.
To be significant. And what you're actually saying then, there's a less than a 5% chance that if I said these two things are significantly different from each other, that I'd be wrong. Okay.
That's what okay.
It's called the false positive, yeah.
Okay.
Yeah. Now, they work perfectly fine as probability. You're splitting hairs between a percentile and a probability. A percentile is actually an area of a unit of measurement. A unit of area. So it's the amount of area under, the curve at a certain point.
Okay.
But it is also synonymous to probability in most every sense, yeah.
Okay. I think I'm good. I think it's, for me, it's just going over it again and again and again.
Yeah.
And kind of sinks in.
Everything, yeah. That's pretty much everything. I mean, it's kind of, I tell, I every now and then I do, sessions on, cognitive theory and cognitive learning and things like that. And, talk about some of the brain theory stuff, and we keep advancing that, but some things hold steady. And one of the things that holds steady is that if you want to learn something, if you want to use whatever language you want to use, if you want to use from novice to expert, if you want to use, from conscious thought to subconscious thought or whatever, it's a matter of repetition. I mean, if you learn to drive, it's a matter of repetition. If you learn to play a guitar, it's a matter of repetition. If you learn to, critical thinking skills, it's a matter of repetition. I mean, you have to repeat things until it becomes subconscious and your mind's, processing all that without you having to think about it. And at that point, you really are, you've kind of learned it. Because you have, and at one time I coached a lot, and I used to tell other coaches, I said, if you don't want kids to have to think about things when they're playing, because if you stop to think about what you're doing, it's too late. The play's by you. I mean, it's gone. The guy's behind you or wherever. You have to be able to think. You have to be able to respond subconsciously. Almost by instinct. Well, it's not instinct. It's subconscious learning. And that's the novice to expert thing, or the conscious to subconscious, and everything is repetition. The more you do it, the better you get at it, whether it's simple stuff or whether it's high level cognitive stuff. It's all repetition.
Okay.
Yeah, I've had to read everything several times for it to sink in.
Yeah, I have a son that's a lawyer, and he's a very successful lawyer, but in the second grade, he wasn't reading. And, they didn't want to test him. And we said, no, we need to test him. And so we pushed on him a little bit, and they did. And he had a learning disability, and it was his ability to organize material and thoughts. And so, his way around things was, to go to his room, and just turn everything off and read things over and over and over again. And then once he did that, then he would never forget it. I mean, he's also got kind of this photographic memory thing where, but he might have to read it 10 times, but on the 10th time, it kind of locks in and he never forgets it. And, it's kind of weird, but,
it works.
It works for him, and everybody's mind works differently. And so you have to find what works for you.
This is cool. Okay, I have one last question that has been bugging me. When you've got a, regular standard curve, right? But you've got something that has like a finite end limit, right? Because technically they never really reach the axis.
Never.
But if you've got something like a test where your students could only score 0 to 100, how like, do we just sort of not worry about that and just sort of ignore it, and in
the real world, in most of the world, you don't worry about that because you hope you develop better instruments. But if you don't really worry about that. But in the scholarly world, you have to make a case for why you might analyze it differently. I was working on something that we had put together for a journal article and a presentation at a national conference, and it ended up being a chapter in a book. But after all of that, but it was there was a distribution that was just that way because the average would have been about a 3 because it was, but the average is actually 4.2 and the top was 5. Now it was normal.
Was that with GPAs, like what you were talking about?
It was kind of with GPAs, and it was normal up to the point to hit a 5, and then hit the wall, and there's no other wall here. There's no further to go, and so you have more variation at the bottom end than you do at the top end, and so we had to make a case for treating that as a binary variable. We found the median, which means half the cases are above, half are below. And we used that as a cut score and just made it instead of 1 through 5, we just made it 0, 1. So it was a binary thing. And we analyzed it a different way, which normally you wouldn't do. And so the first editor that looked at it, I was still writing the part about, making the case for being able to treat it that way. And one of the first people that looked at it, a peer reviewer, I said, well, why would you lose all that variation? And, basically I said, well, just wait a minute, read the next version. Here's the next version. And after he read the next version, he said, okay, he made a pretty good case for that. So that's fine. Yeah, you move on. But in sort of the practical world, you don't really worry about that too much. You just kind of don't think about it too much because most of what you're concerned about really is at those particular finite points that are critical values. Now, if the top critical value is off the scale, there's a little problem there. If the top critical value is 103 and the test only goes to 100, then it's a biased sort of thing, and you'd have to get somebody to tell you how to go through it in a different way so that you can treat it differently. But yeah, it's one of those things that comes up sometimes, but in most of the real world, nobody really worries about it all that much.
Okay, that sounds good.
Unless you happen to get one of those other stats guys that kind of knows stats in and out, and he's going, well, why in the world would you do that? And I'm going, okay,
yeah,
give me a minute. Read the next version and you'll understand. But yeah, it is that's a good question because it pops up fairly often, and most of the time we don't pay much attention to it.
Okay, sounds good.
But it's a sign of a bad instrument. basically.
Yeah. Okay.
Because you really would like instruments to have two things. You'd like to have them a discrimination value, so they really discriminate between people that know something and people that don't know much about
Mhm.
something. And so if it only goes to 100 and the average score is a 95, yeah, it's not going to discriminate very much. And it's one of those things that, a student comes home from college and says, I got a 29 on my physics exam, and their parents kind of go ballistic, and then they say, well, that was a B because the average score was 24.
Right.
And it makes sense because, that scale is discriminating on both ends. And that's what you'd hope to see.
That happened in an organic chemistry class that I was in.
And probably should,
My freshman year.
you really want to separate those folks that ought to be, pursuing a career in chemistry or medicine or whatever, as opposed to those folks that, know test well enough to be able to, kind of do okay.
Yeah. That sounds good.
But no, those are all good questions. I mean, these are good questions. You're a little ahead of the curve here, though, but you're a little, you're thinking about the later questions, and you're also determining for me what the last couple of recordings might look like too. So
Oh, okay. That sounds good.
I record all these things, and then I've got to go back and review them and see, make sure that I get all the pieces in there. Yeah.
That sounds good. So the assessment, just wanted to confirm.
Did I say the 20th?
Yeah.
Yes.
And today's what, 16th? So that's the weekend. I won't get to them over the weekend. I'll probably be the first next week before I get to them. But I'll put up the first I'll check to make sure we've got most of them in, but then I'll put up the answer sheet and a video that kind of walks through that. And then the next time we do a help session next week, I'll walk people through the pieces that they might not quite yet get. Yeah.
Okay. That sounds good.
I kind of know what those are going to be, but it's they're about the same every time. But you might come up with something unique. I don't know. We'll see.
What tend to be the stumbling points that you see?
Just the simple stuff, the things about what defines the 95th percentile.
Okay.
And some of the things that you get out of descriptive statistical output kind of confuse that, like minimum and maximum. That has nothing to do with 95th percentile. It's just lowest and highest score, and the median is just the point at which half are above and half below, and that doesn't have anything to do with the 95th percentile or anything like that either. So it's those types of bits of information that kind of murk things up a little bit. But that's the way it is, unfortunately. I mean, you're always going to have more information than you need to answer most questions you want to answer.
Weeding through that data to figure
out what piece, what things make the most difference. That's why I like JASP. JASP is kind of, it doesn't give you a lot of extra stuff. It's there if you want to click into it and want to do it, but it doesn't give you a lot of extra stuff. So it's kind of, it gives you basically what you need most of the time. Yeah. And not much else. Yeah.
That sounds good.
Y'all guys, okay?
Yeah.
All right. Well, I'm going to click off for a little while and put up a message that I'll click back in about 7 if anybody else shows up. So
thank you
so much.
Stay safe and have a good weekend.
You too.
All right. Bye-bye.
Bye.